Hey guys, Math 6610, following up from the previous video where we talked about type 1, type 2 errors and power. I think the concept, the idea of a type 1, type 2 error and power becomes clear, at least it did for me, when you see it kind of evolve graphically with models and distributions, things that'll play out here in just a second. So that's the purposes of this video. What we're going to do is we've got a situation where we've got a null and alternative hypothesis that what we intend to test. We've got a sample of 40. We somehow magically know that the true population mean is known to be 42. And you know, typically in research you don't know stuff like this, but it makes a good illustration about you know how to calculate a type 1, type 2 error and the power. So we're going to work through this. Now this is not an exercise I would ever give to my lower level statistics classes at the undergraduate level. I do give something like this to the advanced, maybe my stat 3500, but anyway, we'll get to that. But guys, before we go any further, we got a couple things we need to do. First of all, we need to install R, and the installation of R is very easy. I've already brought it up, so you know what I would do is I would just go to Google. What would we do without Google? What did we do before Google? I would just choose R. I remember my secretary one time was like, how do you spell that? Well, you just, you spell it with an R, She was thinking A-R-E or something like that. Once you get to this page, choose, if you have Windows or Mac or Linux, go for it. I have Mac, so I would select this. Now, guys, I use version 3.30. The latest version is 3.41. For now, go ahead and download 3.41 because we're just going to be doing some basic stuff. As we get into more sophisticated models, there are going to be certain libraries and packages that I'm going to want you to install. You're going to install packages and you're going to access the library for those packages. And I'll teach you how to do all that. Some of the packages that I use, I'm not sure work with 3.41. If that comes to be an issue, the solution would be either to go back into the archive and download 3.30, or find an upgraded package that does what I do with the old package. So we will cross that bridge when we get to it. So anyway, guys, when you download R, it's going to ask you to choose a CRAN, C-R-A-N. What I want you to choose in the installation process is use the first one under USA, and I think it's called like California 1, CA1. So just so we can, it doesn't matter. It's just I want everything to be consistent so we can do the best to minimize issues. So guys, once you get R downloaded, it's going to look like this. And this is the statistical software package that we're going to use to do our computing. Now, let me get out of this and show you a couple of functions that we're going to use in R that are applicable to finding probabilities of type 1 and type 2 errors and power. Now, the four distributions that we're going to run into the most, that we're going to use the most, and I talked about this in the previous video, are the normal distribution, the t distribution, the f distribution, and this chi-squared distribution. Now, on R, we have two functions that allow us to do kind of opposite operations. we have what's called a P function. Now, what a P function does is it finds the probability or the proportion of the area that's shaded to the left of a particular value, given a mean and a standard deviation. So, if we have that IQs follow a normal distribution with a mean of 100, standard deviation 15, and we'd like to know the probability of randomly selecting someone who has an IQ greater than 112, we could use this P function in R to work this problem. Well, since this comes from a normal distribution, we're going to use Pnorm. If we were working with the T distribution, we would use PT. If we're working with the F distribution, we're going to use PF. If we're using the chi-square, we're going to use P chi-square. What these functions do is we have a value from the distribution, then we have the parameters. Now that's either the mean and the standard deviation or the degrees of freedom for these distributions, so we could have one or two parameters, and then it gives us the value. So let's see how this works in R. Let's see how that one works. Shoot. So let's go to R. So if I want Pnorm, and I want the area left, oh, I'm greater than 112, right? So if I put in 112 with a mean of 100, standard deviation of 15, this is going to give me the area to the left of it. So guys, for me to find the area to the right, I'm going to have to go 1 minus that value to get the area to the left. So the probability of having, to get the probability above. So the Pnorm at 112, the one I've just highlighted, that gives me the area to the left as a default. If I want the area to the right, I have to subtract that value from 1 to get the other side of the distribution. Now, what if I had a T distribution and I wanted to find the area to the right of like T equal 1.28? Then I would use PT. If I put in 1.28, that's going to give me the area to the left. So I'm going to come in and go 1 minus that to get the area to the right. And then I would put in the degrees of freedom. Let's just say the sample size is 40. The degrees of freedom would be 39. So the area to the right of 1.28 is about 10.4% of the area under the curve, or the probability of selecting a value from this distribution 1.28 or higher is 0.104. Now, what about the F distribution? Well, the F distribution, let's say we want the area to the left of a F value of 2.58. Well, then we can just use PF, 1.58, because we want to the left. If we wanted to the right, we'd have to come over here and do 1 minus. Now, the F distribution depends on 2 degrees of freedom. And I'll get into all that later on, but let's just say the 2 degrees of freedom here were 216. So the area would be 0.76. And chi-square works the same. So we're going to have lots of opportunities to work these types of problems. Now, let me get out of here and demonstrate another function in R. It's called the Q function. Now, depending on the distribution that we want to find or use the Q function, it could be norm, it could be T, it could be F, or it could be chi-square. The value that goes right here is actually the value from the distribution guys, I'm wrong on that. It's the area to the left of the value from the distribution that we're interested in examining or finding. What goes out here? The parameters. The mean and the standard deviation if we have the normal distribution. Degrees of freedom if we have the t, f, or chi-square distribution. So what this tells me is, let's say, for example, we'd like to know what IQ represents the 80th percentile. Well, getting a picture of this, IQs are represented by a normal distribution. Mean of 100, standard deviation 15. So we know that in the middle of the distribution we have a mean of 100, standard deviation 15. So right up here where the second derivative is equal to 0, we know that we can add 15, subtract 15, and continue to do that 2 or 3 in each direction. But what we want to know is, we want to know what IQ is the 80th percentile. Well, percentile just is what percent at or below. So somewhere out here there is an IQ that has 80% of the distribution to the left of it or below. Now, contrast and compare that to the key that we had a while ago, the P key. The P key works the same way as the Q key, except the P key takes a value and finds this area. The Q key is given the area, and you're trying to find the score from the distribution that corresponds to that. Well, the Q key is really simple. Q, the distribution that you're, the underlying probability distribution you're using, the area to the left, and the parameters. All right, so for this problem right here, what IQ represents the 80th percentile? Guys, it's going to be easy. We're going to do Q norm. Area to the left is 0.80 or 0.8. Mean of 100. Standard deviation 15. So the IQ that represents the 80th percentile is 112.6. Now, switch it up a little bit. We have a t-distribution. Sample size is 65. We want to know what t-value from this distribution has 22% of the scores to the left of it, or 78% of the scores to the right. So what are we going to do? Well, we're going to use the Q function because we want to find a value from a distribution that has this characteristic. So we use Q. What distribution are we using? The t-distribution. What goes first? Percent below. What goes next? The parameters. What's the parameter of a t-distribution? The degrees of freedom, n minus 1. So QT, easy for you to say, to find that. So we've had 0.22 to the left, degrees of freedom 64. So the standardized score would be negative 0.78. Now that makes sense. It might have kind of alarmed you at first to think that you got a negative. But remember, in the t-distribution, The mean is 0. So all these values to the left are negative, and all these values to the right are positive. Now, that's not the same with the F distribution. The F distribution, depending on the degrees of freedom, is going to look something like this. And I can tell you from experience that this would probably be close to the F distribution, degrees of freedom 2, 25. Now, what if we want to find an F value right here that has 10% of the distribution to the right of that? Well, what are we going to use? Well, since we're trying to find a distribution, since we're trying to find a value from a distribution that has a certain characteristic, we're going to use Q. Next thing we're going to do is put in the distribution. Next thing we're going to do, put the area to the left. Next thing we're going to do is put in the degrees of freedom. So I can go to R, and I can go QF, 0.90, degrees of freedom 225, and I will find that that value is 2.528. Now, what if we're like, what if we're kind of cynical and we don't believe that? Well, let's see if truly there is 10% of the area to the left of 2.528 using the other key. So the other key would find the probability, so we can use PF. And since we went to the right of 2.52, we'd have to go 1 minus. Remember the default, if we just put the value in, it finds the area to the left. So no, so we don't get into any wackiness, I'm going to go ahead and just type out the whole 8305. Degrees of freedom 225. Now, if the previous answer is right, what should we get here? Well, we should get the area to the right because we subtracted from 1, so we should get something close to 0.10. Pretty good, 0.1. All right. Now, we got some tools, at least a few tools, enough to be dangerous. Let's work the handout. All right, Math 6610. So we're given a sample size of 40. And so this tells me that the degrees of freedom are equal to 39. And I want to test the null that the mean is equal to 40 against the alternative, the mean is greater than 40. When I see this, I think two things. First of all, I'm conducting a one-tail test. Greater than, less than, or one tails. Two-tail tests are not equal to. The next thing that I notice is because I'm testing a value, a claim about a population mean, then I know I'm using a t-test. If I was making a claim about if the null and alternative hypotheses had to do with the quality of population means over more than two groups, then I would use the F distribution. I would use an F test. So reading further here, if the true population mean is known to be 42, then what is the probability of committing a type 1, a type 2, type 1 error, type 2 error, and power? Well, guys, to work this, we need a really good drawing. So this is the hypothesized distribution, so we kind of assume we are drawing from this distribution unless there's reason to suspect that we're actually drawing from another distribution. And this distribution right here has mean equal to 40. So I'm going to call this my hypothesized distribution. But for illustration purposes, and not something that would ever happen in research, This just makes a nice illustration for visualizing type 1 and type 2 errors and power. We've got this information just popped up. We know that the true population mean is equal to 42. So this is the true distribution. When conducting this test, we go in and take a sample. We assume our sample's coming from this distribution, but it's really coming from this distribution. All right, question number 1. What's the probability of committing a type 1 error? Well, guys, this is up to you. The probability of committing a type 1 error is alpha. Alpha is the level of significance for your test. We usually set this at 0.05. Since I'm conducting a right tail test, in this distribution right here, my rejection region is going to be in the right tail. If this had been a less than 40, my rejection region would have been in the left tail. If this had been not equal to, we would have done a two-tail test. I would have split my rejection region. If it's alpha equal 0.05, I would put half in this tail, 0.025, and I would put half in this tail, 0.025. That's not what I got. I have greater than 40, so I'm putting all of my rejection region in the upper tail. So I need to come in and find what t-value separates the fail to reject region and the reject region. Well, guys, I'm going to use R to do that. So I have 0.05 up here, because that's my alpha. It's probability of committing a type 1 error. It's the proportion of the area under the curve that I put in my rejection region. And then this is going to be 0.95. Now I'm using the t-distribution, so what do I need to use? Well, I want QT. I want the area to the left to be 0.95. And I have degrees of freedom 39. Or if I didn't want to do it that way, I could do 1 minus QT, 0.05, 39. No, I couldn't do that. That only works with the PT. Guys, that's one of the dumbest illustrations I've ever done. Please forget that. I might even edit it out. That's embarrassing. That doesn't work. Now, if I had PT, that would work. QT does not work. I would. That's just silly. That's just silly. So 1.685 is going to be the determining factor, the cutoff between reject and fail to reject. So if I get a test statistic above 1.685, it's going to fall in this region, I reject. If I get a test statistic less than 1.685, it's going to fall in this region, I'm going to fail to reject. However, 1.685 and 40 are on two different scales. So I need to get this thing back to the original scale using a formula that we used way back in undergrad called a z-score formula. Typically we saw z equals x minus mu over sigma, but since we're dealing with a sampling distribution, t will be equal to x bar minus mu over the standard error. Guys, our standard error in this case will be the standard deviation over the square root of n. So I'm not given the standard deviation, so and I should have included that. So let's just say that we have a standard deviation equal to 5, just for illustration purposes. Okay, so working this out, I have t equal to x bar minus mu over the standard deviation over the square root of n. So my t for cutoff is 1.685. We're trying to find the sample mean that corresponds to that. In the distribution, it has a mean of 40 and a standard error of, what did I say, 5? Yeah. Over the square root of 40. So x bar, I'm going to put that in my calculator real quickly. So 1.685 times 5 divided by the square root of 40. And then add 40. So the sample mean is 41.33. So the sample mean that represents this is 41.33 in this distribution. But from this distribution, the one that we are truly drawing from, that t-score is going to be different because it's coming from a mean of 42. So from this distribution, what's the t-score? Well, we use R to find that, don't we? So we know that the sample mean is 41. It's going to be below the 42, so we're expecting a negative t-value. So I'm going to use the same formula. My t is going to be the sample mean minus the population mean over the standard error, which is 5 over the square root of 40. So my t distribution, or my t-score that cuts off the, is 41.33 minus 42 divided by the quantity 5 divided by the square root of 40. So it's negative 0.847. In this distribution. Now, let's do some calculations. Let's go back to our drawing here. We know that the probability of committing a type 1 error, because we control that, is 0.05. That's the level of significance we state at the beginning of the test. What's the probability of committing a type 2 error? First of all, where is the area shaded? Well, the calculation has to be from the distribution that we are truly drawing from. So it turns out that the probability of committing a type 2 error is that part right there. Now, first of all, why isn't it all this other stuff? First of all, we're truly drawing, we're testing this distribution right here. We think we're drawing our sample from this distribution, and we're going to fail to reject the mean of 40 if we get something close to 40. But we kind of have a luxury here, and trust me, this doesn't happen in research, but we have a kind of a interesting caveat here that we know the mean is 42, so we are truly drawing from this distribution. So any calculations on our probability of a type 2 error have to come from the distribution from which we are drawing. So it has to come from here. Well, anything to the right of this line right here is going to lead in rejection. But a type 2 error, by definition, is failing to reject a false null. So if we get something over here, we are going to choose fail to reject. That's going to be the decision because we're left of the decision point. But the true probability of committing a type 2 has to be calculated from this distribution because this is the one that we are truly drawing from. So how are we going to find this? Well, we've got to have this t-score because this is the distribution we're truly drawing from. So we have to use that in our calculation, and we need to find the area to the left of that. Well, guys, that results in area to the left, PT, negative 0.847, degrees of freedom, 39. So the area to the left of that is 0.201. So what does that tell us? This area right here is 0.201. So that tells me that the probability of a type 2 error is 0.201. Taking me to my third question, what's the power? Well, guys, we know the power is always 1 minus beta. This 0.201 is equal to beta. So the power is just 1 minus 0.201. And if everybody's okay with that, I'm just going to call that 80%. So this part right here is actually the power of your test. And again, that calculation has to be made in this distribution because this is truly the distribution that we're drawing from. So we have a 0.8 probability if this claim of mu equal 40 is not true. It's false. Because we're drawing from this distribution, we have a 0.8 probability of rejecting this claim because anything in this distribution right here that we think we're drawing from would be right of our decision point. So it would result in a rejection, but our calculation of the power has to come from this distribution because this is the true distribution. So what's the power? Well, technically, the way we've rounded it would be 0.799. I'm okay with 80%. All right, part 2, rework the problem conducting a two-tail test. So I'm going to turn things this way. I don't guess it really matters. So in this test right here, in this distribution right here, the mean is equal to 40. But it's a t-distribution, degrees of freedom, 39. I'm going to be consistent, set the probability of a type 1 error at 0.05, but I have rejection region in both tails now. Half of that rejection region, 0.025, in the left tail, half of it in the right tail, 0.025. Because the true distribution is greater than the hypothesized distribution, I really don't need to worry about this down here. I need to worry about this up here. Now we'll come back. Does that ever play a role in our calculation? We'll talk about that in just a second. So this 0.025. So I need to come in here and find the t-critical. That's the decision point for the hypothesized distribution. And I need to find the sample mean that separates the fail to reject and the reject region in the hypothesized distribution. So guys, we should be good at that by now. We can go to R. And I would know that I need QT 1 minus 0.025. So I need the area to the left. Degrees of freedom 39. So 2.023 is the T critical. So now my X bar, I'm going to get another sheet of paper. So again, using T equal X bar minus mu over the standard deviation over the square root of n. So my T is 2.023. I need the X bar that corresponds to that, mu. So that's going to be distribution with mean 40, the hypothesized distribution. We assumed a standard deviation of 5 over the square root of 40. So guys, X bar is going to be well, that was real clever. I was typing numbers in my calculator, and my calculator wasn't even turned on. So 1.5999 plus 40. So 41 point. I'm just going to call it 41.6. That's so. This is the critical information from the distribution that's hypothesized that we think we're drawing from. Now we need the location of this value in the distribution that we're truly drawing from. So we have 41.66, so the T distribution in the, let's just call it the true distribution. So it's going to be 41.6 minus 42 over 5 divided by the square root of 40. So I get negative 5 or 0.506. For this distribution. All right, gang, what we got? We've got this part. This goes on out this way, right? So probability of committing a type 1 error is going to be that area, and we know that's 0.025. Now, what's the probability of committing a type 2 error? Well, that's going to be this little sliver right here. Again, it has to be calculated in this distribution because this is the distribution that we're truly drawing from. So because we have to make our calculations from this distribution, we need the area to the left of T equal negative 0.506 in the distribution degrees of freedom 39. Well, all right. So we need PT, area to the left, negative 0.506, degrees of freedom 39. So our probability of a type 2 error is 0.308. Which I've done up here. So this tells me that my power, now again, think of this as beta. Think of this as alpha. So my power is going to be 1 minus my probability of committing a type 2 error. So what is that? 692.692. So notice that from switching from a one-tail test to a two-tail test, my power goes down from 0.80 to about 0.70. And the reason being is this decision line is moved this way, when we put more area to the right, so if we do a one-tailed test, we put 5%, not half of 5%, the area to the rejection region, which decreases the probability of a type 2, but increases the remaining area under the true distribution, which is called our power. Now, the final question that I have here is provide a sketch of the two distributions and shade the area that correspond to a type 1, type 2, and the power. So essentially what I've got is I've got this one distribution that is hypothesized. I've got this other distribution that we are truly drawing from. And I'm going to do this demonstration on a right tail test. So in this distribution right here, I've got some cutoff that gives me a type 1 error. Now, why is that a type 1 error? A type 1 error is what? Rejecting a true null. Well, if this is true, then our calculations have to come from this distribution. So we're rejecting, so this area out here would be too far away from the hypothesized value. So the value in the null would be true, which kind of contradicts the way I'm setting up this model. But this would be too far away from the hypothesized value. So under the assumption that this is a true value, this would lead in an error, an incorrect decision, because we would think we were too far away from the true value, hypothesized value, to conclude this is true. So that's why that's a type 2 error, or type 1 error. This right here in this distribution is the probability of a type 2. And again, remember the definition of a type 2 error. Mu is false, H sub O is false. If it's false, it's got to be something else. So we're assuming here that the something else is the mean is equal to 42. So the probability of what we collect has to come from the true distribution that we're actually drawing our sample from. But if we get anything from here over, it's going to make us think that it's close enough to the hypothesized value. So by definition, a type 2 is failing to reject, because it's on the left side of the rejection line, a false null. But again, the calculation for the probability has to come from this distribution, because this is truly what we're drawing from. Again, this is false. It's got to be something else. Now, let me see if I have a red ink pen. Usually professors keep red ink pens, right? So guys, what is the red? That is the power of your test. All right. Cool stuff, right? Maybe. All right. In the previous video, I told you that we would work, let me bring it up, we would work some problems. Let me see if I can find them. Yeah. If you go to the to the video, at least the PowerPoint for the previous video, there were some things we said we would work. So z equals 1.45, one tail, h sub a greater than. The second one was t equal negative 2.12, one tail. H sub a less than n is 52. The next one is t equal negative 2.12, two tail. Sample size n equal 52. So since it's two tail, we know that h sub a is not equal to. So this is the first one, this is the second one, this is the third one. The fourth one is f equal to 3.98. And let's just assume that the degrees of freedom for the numerator is 5. And degrees of freedom for the denominator is 12. In 5, we have a chi-square value of 5.95. And let's just assume that degrees of freedom is equal to 4. Now, the degrees of freedom weren't given, but we got to have the degrees of freedom or we can't work the problem. So what's this going to look like? This is going to look like, in a normal distribution, since we're one tail, we want 1.45. We need the area to the right in the normal distribution. So I got a meeting in 10 minutes, so I got to get busy. All right, so what I'm going to do there is I need the area in the right. So I'm going to go 1 minus Pnorm, 1.445, mean is 0, standard deviation 1. So it's already been standardized. So the p-value there would be 0.074. All right, I'll tell you what. Let's go split screen here and save some moving around. All right, to the right we have t equal negative 1.2. So what we got here is in the t distribution, degrees of freedom 51. Negative 2.12. We're doing a left tail test, so we only worry about the area in the left tail. Sample size 52, degrees of freedom 51. So since I want the area below, I'm just going to use PT. Negative 2.12, 51. So the p-value there would be 0.019. Now, a little different here, doing a two-tail test. So we have two tails that we have to contend with. So what we ultimately have to do in a two-tail test is we have to find the area to the left of 2.12, but we also have to find the area to the right of positive 2.12. Two-tail test, we kind of give the same likelihood in both ends of the both tails of the distribution. So again, we've got two tails to consider. We split our alpha level in half and put half here and half there. So when we calculate our p-value, we have to multiply by 2 to accommodate splitting the alpha value. So what I'm going to do is I'm going to find this area right here. Because of symmetry, I know this area is the same as this area, so I'll just multiply by 2. So what do I need? PT, negative 2.12. Okay, you held the laugh because all I had to do is multiply the previous value by 2, and I get 0.039. All right, the F distribution. Guys, remember the F distribution is kind of a positively skewed distribution, and all we care about in the p-value for the F distribution is the area above. There's no wackiness above, below, multiply by 2. The F distribution is always the test statistic, the area to the right. So to work this, I'm going to use 1 minus PF, 3.98. And the degrees of freedom we're using for this illustration are 5 and 12. So the p-value here, we would have statistical significance. It's 0.023. For an F statistic of 3.98. Chi-square statistic works the same way. Chi-square statistic is also kind of a right-skewed distribution. So at 5.95, again, just like the F distribution, we only want the probability to the right of 5.95. So again, I'm going to have to go 1 minus chi-square, 5.95, degrees of freedom 4. Okay, oh shoot. Okay. Huh. Guys, I don't remember the, this is embarrassing. Okay, let me jump over here and find it real quick. So I'm obviously doing something wrong. Okay, it looks like chi-SQ, that's what I had. Oh, shoot. Guys, I'm being crazy here. 1 minus p chi-square. All right, this will work. So the p-value is 0.203. So a chi-square statistic of 0.595 degrees of freedom 4 would not be statistically significant. All right, guys, sorry about that. That's just one of those things, and it's certainly not worth redoing the video for a bonehead moment. Heck, I think I had a bonehead moment earlier in the video. So, guys, that's all I got. This video lasted a little longer than what I hoped, but I hope it was useful. Take care.